Hello, and welcome to my summary of electric fields. Electric fields are the area of effect of electromagnetic force that emits from a point charge. The electric field is often visualized by arrows that signify the direction and magnitude of the field. In this first example, the positive charge is a repelling force and the negative field is an attracting force, as demonstrated by the direction of the arrows for each charge. But how is a field charge created in the first place? Let's look at the atom. Protons have a positive charge and electrons have a negative charge. The charge is positive if there are more protons, negative if there are more electrons, and neutral if they are even in value. Charge is measured in coulombs, and a single electron has a charge of 1.60 times 10 to the negative 19th coulombs. When two objects are rubbed together, some of the electrons transfer over to one object, giving it a negative charge, and leaving the other with a positive charge. This is called the triboelectric effect, and it creates static electricity, which in turn creates electric fields around the charged object. To apply this idea to real life, let's play with balloons. If you rub a balloon against a sweater, the sweater tends to lose electrons and become positive. The lost electrons stick to the balloon and make it negative. Both items are charged now and have electric fields. Since opposite charges attract, the balloon sticks to the sweater. Also, since the sweater is all positive, individual fibers stand on end and separate as the like charges repel each other. Items can become charged by contact, as seen here, or by induction, when a charged object draws the opposite charge toward it and repels the like charge to the opposite side of the item, separating the charges and charging the item. Now, let's analyze the effects of electric fields on a smaller level. In the first example, a positive field pushes a positive charge to the left, since like charges repel each other. When another positive field is added on the left, though, in example B, the charged point is caught in the middle with no movement, as the force of both fields cancel each other out. However, if we move to example C and a negative field is placed above the positive charge that is caught between the two positive fields below, the charge moves upwards to approach the oppositely charged field and its attractive force, as the two positive fields still cancel each other out as the third negative force is added above it. All these electric fields exert electromagnetic force on these charged particles. We can find the magnitude of these points mathematically by using the equation E equals K times Q over R squared. E is the strength of the electric field, and it's measured in newtons per coulomb. K is Coulomb's constant, which is 8.99 times 10 to the 9th. Q is the absolute value of the point charge that emits the electric field, highlighted here in yellow. R is the distance highlighted in purple between the center of the field and the single charge the field acts upon. Per the diagram, you can see the electric force decreases exponentially further the charge moves from the field. This equation only calculates the effects of one part of the field on one particle. If we were to add another field directly below the green charge, we would have to calculate the force of each field individually and then use the Pythagorean theorem to combine them and find the total strength of the two fields on one single charge. So, in summary, the transfer of electrons to certain materials creates charges, and those charges create electric fields that exert force on the charges of other objects. The direction of the fields and the force they exert is determined by the attraction of opposite particles and the repulsion of like particles. Finally, the equation E equals K times Q over R squared is used to calculate the force and strength of an electric field on these charged particles.